conic sections in polar coordinates. So we're in our last section, 9.7. Talking about conic sections in polar form. So we want to, I'm going to give you a definition. Our definition will be a little bit familiar. Another way to define conic sections, and the way that we're defining them today will let us works nicely with the conic sections of polar coordinates. So we're going to say that a conic section is the locus of points and again, a locus is just a collection, a set that shares some property. The locus of points where the distance from a fixed point, and our fixed point is going to be our focus, is in constant ratio with the distance from a fixed line. Oh, and I forgot one thing, the constant ratio is the eccentricity. So our eccentricity is our constant ratio with the distance from a fixed line. And our fixed line is the directrix. So for conic sections in polar coordinates, all of the conic sections have a directrix. When we talked about conic sections in rectangular coordinates, we only talked about the directrix with the parabola. So with this definition, all of the conic sections have a directrix. When we're talking about conic sections in polar form, one of the foci is going to be the origin. We're always going to put the origin as our foci. So in polar form, our equations work out really nicely if we put one focus at the pole, at the origin. And I guess I should say origin, and in polar coordinates we call that the pole. So we're going to put one of our foci at the pole. In rectangular coordinates, it was very convenient if the center of our conic section was at the origin, or the vertex of the parabola. We can think of the center and the vertex of the parabola as the same thing. So in rectangular coordinates, it's nice if the center is at the origin. In polar coordinates, it works out nicely if our focus is at the pole. And every conic section is going to have a directrix. And this ratio of the distance from the focus and the directrix is our eccentricity. And for an ellipse, do we remember how large the eccentricity was for an ellipse? E was less than 1 for an ellipse. A parabola? We didn't really talk about the eccentricity of a parabola, but for a parabola, the eccentricity equals 1. And for a hyperbola, the eccentricity is greater than 1. So the eccentricity is a little more important when we talk about conic sections in polar form. And each of the conics is going to have a directrix. So the directrix for a parabola is just like we talked about the directrix before. The vertex is halfway between the focus and the directrix. Everything's the same with the focus and the directrix with the parabola. If I draw a little sketch of an ellipse, since we have our origin at the pole, our axis is always going to be either the polar axis or the pi over 2 axis. So that makes it convenient to work with these as well. And so if we draw an ellipse, one focus is going to be at the pole. So our ellipse, we had a horizontal ellipse. It would look like this. One focus is at the pole, and our directrix would be this line over here. And our directrix is always going to be at the end that's closest to the pole. So that would be the directrix for this horizontal ellipse. And for a hyperbola, the directrix is in between the two branches. So for our hyperbola, one focus is at the pole, and the other branch would be over here, and our directrix would be in between the two branches. And it's always, our directrix is going to be closer to the branch that has its focus at the pole. So the directrix is not directly in the center of the two branches, so the directrix doesn't go through the center. It's a little closer to the pole. But our directrix is between the two branches. So this gives us a little visual of what we're talking about. And we make a ratio of the distance from the point to the directrix and to the focus. And that directrix is constant. For an ellipse, it's always less than 1. For a parabola, it's always equal to 1. And for a hyperbola, it's always greater than 1. Which is an alternative way to define a conic section. All right, we're good so far. We want to get to the fun stuff. We want to get to the equations, how we work with them. All right, so in a conic section, when we use this definition, when we have one focus at the pole, our conic sections are always going to look one of two ways. Basically, we have two equations. So our equations are going to be R equals EP over 1 plus or minus E sine theta, or R equals EP over 1 plus or minus E cosine theta. One of these two equations with a plus or a minus is going to give us a conic section. P, the absolute value of P, tells us the distance between the focus and the directrix. So that's what P tells us. So E shows up in our equation, our polar equation for a conic, and P tells us the distance between the focus and directrix. So before we start working with these equations, let's look at them and let's think about them for a little bit. This polar equation only has a sine theta in it. What kind of symmetry is it going to have? Pi halves. It's going to be symmetrical about the pi halves axis. So if our polar conic is equation in this form, it's going to be vertical. Our axis is going to be vertical because it's going to be symmetrical about the pi over 2 axis. And because this equation only has a cosine theta in it, it's going to be symmetrical about the polar axis. So this would give us a horizontal conic section. So our axis would be horizontal for this. So we can pick out very easily whether it's vertical or horizontal. And since this equation is going to give us a vertical axis, our directrix will be horizontal. Because this one has a horizontal axis, our directrix will be vertical. So we already, just by looking at the form of the equation, we can pick out a lot of information about it. Questions so far? These equations are really nice to work with when we can work with them in this way. So let's take a look at a couple of examples of how we're going to use these equations to look at conics. Okay, so let's say we have an ellipse. We want to find the center, the foci, and the vertices of this ellipse r equals 15 over 3 minus 2 cosine theta. All right, so before we start working, vertical or horizontal major axis. Just a cosine theta in there, so it has what kind of symmetry? Polar axis symmetry. The polar axis is horizontal, so our focus, one focus is at the pole. So this is going to give us a horizontal ellipse. So our axis is horizontal. So that tells us that our ellipse is either going to look like this, since one focus is at the pole, or it could look like this. So it's going to look like one of these two, but our one focus is always at the pole. The vertices are extremely easy to figure out. How can we figure out where the vertices are? What angle is this? 0. One vertex is going to be when theta equals 0. One vertex is going to be when theta equals pi. Plug in theta equals 0, I get one vertex here or here. Plug in theta equals pi, I get another vertex here or here. So we get a vertex, when theta equals 0 and pi. If it were a vertical ellipse, we'd get one vertex at theta equals pi over 2 and one vertex at theta equals 3 pi over 2. Really easy to find the vertices. Same thing with hyperbola. Same thing with a parabola. We just decide which axis we're on, and that angle is going to tell us where the vertices are. So we're going to plug in theta equals 0 and theta equals pi. When theta equals 0, we get r equals 15 over 3 minus 2. The cosine of 0 is 1. So we get 15. So our point 1 vertex is at the point 15, 0. And remember, we're in polar coordinates, so this is r and theta. And then we're going to plug in theta equals pi. So r equals 15 over 3 minus 2 times cosine of pi is -1. So we get 15 over 5, and we get 3. So we also get a vertex at 3 pi. And remember, this is r theta. So our ellipse is going to look like this one. So it's not this one. So this is 15, 0, and that point is 3 pi. So that's our ellipse. So there are vertices. Where's the center? Halfway between the vertices. Our center is always halfway between the vertices, just like when we worked with ellipses before. So our center, what point is halfway between 15, 0, and 3 pi. We could think of this as negative 3. What point is halfway between 15 and negative 3? Nine, 3, 6. Some multiple of 3. The midpoint between the point, we can think of this as x equals negative 3. So between 15 and negative 3 is, what is it? 6.6. So our center is going to be at the point 6, and what's our angle? 0. Center is at 6, 0. Halfway between 15 and negative 3 is 6. All right, so we're almost done. Where's one focus always with our polar form? At the pole. So our center is 6, 0. One focus is at 0, 0. What information do we get from this? C equals 6. If we're thinking about how we worked with ellipses before. So if our center is at 6, 0, one focus is at 0, 0, where's the other focus? 12, 0, 6 units the other direction from the center. So there we are. We found our vertices by plugging in 0 and pi. Our center is halfway between the vertices, and one focus is at the pole. The other focus is 6 units in the positive, or 6 units along the theta equals 0 axis towards the other vertex. So there we go. There's what the question asks us to find. Questions there? Isn't this nice, easy to work with? You don't have to do as much stuff to figure out stuff about this ellipse. It's also nice that the axis is always going to be on theta equals 0 or theta equals pi over 2. All right. A couple of other things about our polar form that will give us some more information about our graphs and how we can work with our graphs. So the plus and minus sign tells us which side of the pole our directrix is on. So we know we're going to have a horizontal axis here, but the plus or minus tells us what side of the pole our directrix goes on. So let's write down those rules. So if we have r equals EP over 1 plus e sine theta, we know that this is going to have a vertical axis, going to have pi over 2 symmetry. So we're going to have a horizontal directrix above the pole. So plus sign tells us that we're above the pole. And it's just the opposite if we have the minus sign. So we know because this is a sine function, that we have pi over 2 symmetry, so our axis is vertical. Our directrix has to be horizontal. Plus sign tells us above the pole. Minus sign tells us it's below the pole. Same relationships with the cosine form of our conics. So if we have r equals EP1 plus e cosine theta, we have a vertical directrix because our axis is horizontal. To the right of the pole. and then we switch it around if we have a minus sign. So this just gives us another way to work with these equations. And if we are given some information about our conic section, we can come up with, it gives us some tools to come up with an equation for our conic section. So if the problem says we want to find the equation that of the whatever that has a focus or vertices at these points and a horizontal directrix below the pole, we can come up with an equation. And that's the examples I want to do next. Oh, this one should be minus. Thank you. I meant to switch them. Thank you. All right, so let's take a look at how we can use this information to help us with certain kinds of problems. All right, so let's say we want the polar equation of a parabola with our focus at the pole and directrix x equals -4. All right, so first off, the line x equals -4, is that vertical or horizontal? It's a vertical line. Is it to the left or the right of the pole? X equals -4 is left of the pole. So we know that our equation is going to have the form r equals EP over 1 minus E cosine theta. So we already know that our equation is going to have this form. What's the eccentricity of a parabola? 1. The distance from the focus to the pole is how many units? 4. P equals 4. So our equation, R equals 4 over 1 minus cosine theta. So just given those two pieces of information, we have an equation for this parabola. Pretty nice. We good with that example? The equations are really nice to work with. All right, let's look at one more example with a hyperbola. Where we have to do just a little more work. Still very nice and easy to work with. Where we have to do a little more work because for hyperbola we can't just figure out that E equals 1 right away. We have to do a little more work. All right, so for this one, last example, we want the polar equation of the hyperbola with vertices (1) 3 pi over 2 and 9 3 pi over 2. So let's draw a quick little sketch to help us visualize this. Here's the point 1, 3 pi over 2. One focus is at the pole, so there's my pole. And one point is down here at 9, 3 pi over 2. So there's a very rough sketch of my hyperbola. The directrix is going to be here. So we've already got a bunch of information about about our equation. We have a horizontal directrix below the pole. So our equation is going to be in the form R equals EP over 1 minus E sine theta. So we already know that that's going to be the form of our equation. We can use the information that we have here. So what we need to do is find E, and we need to find P. To find E, to find our eccentricity for a hyperbola, what piece of information do we need? C and A, right? E is C over A. So we need to find C and A. So we need to find the center. Where's the center? Halfway between the vertices. What point is halfway between 1 and 9, 3 pi over 2? 5, 3 pi over 2. Halfway between 1 and 9 is 5. So the center is at 5, 3 pi over 2. So our center is in here. So what piece of information does that give us? Actually, that gives us everything. How far is it from the center to a vertex? 4. So what is that? What does that give us? A equals 4. One focus is at the origin, or at the pole. So what does that tell us? Distance from the center to the focus is 5. C equals 5. So we know that E equals C over A by fourths. Check our work. We know that the eccentricity of a hyperbola is supposed to be bigger than 1. By fourths is bigger than 1. So we're good there. So let's plug this into our equation. R equals 5/4 P over 1 minus E sine theta. Oops, 1 minus 5/4. And I want to simplify this a little bit. I want to simplify this. So I'm going to multiply. I'm going to get rid of that fraction. So I'm just going to multiply the top and the bottom by 4. So I can rewrite this as R equals 5P times 4 minus 5 sine theta, just to make it a little easier to work with. Now we need to find P. How can we find P? Plug in one of the points. We know these points are on our hyperbola. This is an R and this is a theta. Plug in a point. So we're going to plug in 1, 3 pi over 2, because that's nice and easy to work with. So we get that 1 equals 5P times 4 minus 5 sine 3 pi over 2. What's the sine of 3 pi over 2? Sine of 3 pi over 2? Down here on the negative y-axis, the y component, negative 1. So I get that 1 equals 5p over 9. And from this I get that p equals 9/5. So substitute that back in, and finally I get that my equation is R equals, when I put that in, 9 times 4 minus 5 sine theta. So similar to working with hyperbolas and ellipses and parabolas in rectangular coordinates, but in a lot of ways, the information comes out of these equations much more easily. We don't have to work with them so much. We don't have to do so much with them. It's also nice that one focus is always at the pole, and that our axis is always either the pi over 2 axis or the theta equals 0 axis. All right, questions on that example? Okay, I forgot to mention one thing. Let me go back really quickly, or just to look at another quick, just talk about this one really quickly. What if we wanted just to identify what type of conic? And we had an equation that looked like this. R equals 12 over 3 minus 4 sine theta. And we wanted to know what kind of conic section that was. What do we need to determine from the equation to decide what kind of conic section it is without converting it to rectangular coordinates? We need the eccentricity. We need to find E. That's what this question is really asking us. Can we pick E out directly from this equation? There's one thing that we need to remember. In our polar form of our conic equations, what is this number always? 1. So we need to get a 1 there. How can we get a 1 there? Divide everything by 3. So I want to multiply the numerator and denominator by 1/3. So I get R equals, divide everything by 3, I get 4 over 1 minus 4/3 sine theta. So E equals 4/3. And 4/3 larger than or smaller than 1? Larger than 1. So this is a hyperbola. And then really quickly I wanted to graph this in the calculator. Polar graphs of conic sections actually turn out kind of nicer than rectangular graphs. So let's graph this. Go to y equals, clear that out. And I'm going to do zoom 6, zoom standard. So I'm going to graph, what was our equation? 12 divided by 3 minus 4 sine theta. Graph that. Theta max, this looks okay. That's minus 10. What did I don't know what I did here. 12 divided by 3 minus 4 sine theta. So there's the upper part of the hyperbola. These are the asymptotes. There's the hyperbola. Let's expand the window a little bit. So let me get my y window to go down a little further. Let me go to minus 20. So there's my graph of that hyperbola in polar coordinates. The bottom branch, the upper branch, the asymptotes. So we get a really nice graph of this in polar coordinates. The graph turns out really nice. So in a lot of ways, graphing conic sections in polar coordinates is a little nicer, a little easier than graphing in rectangular coordinates. And we don't run into the problem where our parts of our graph don't show up. All right, questions? Okay. Homework. All right, there we go.